happy to have Akhila Mohan in this coffee talk today, and she will be talking about uniqueness of Galilean conformal electrodynamics and its dynamical structure. Please go ahead.
Thank you. First of all, I would like to thank the organizers for giving me an opportunity to talk here. My title of the talk is Uniqueness of Galilean Conformal Electrodynamics and its Dynamical Structure. And this talk is based on the work with Kinjal Banerjee and Rudranil Basu in this arcane number. And let me introduce the outline. So first I will be giving introduction to the Galilean world, and then we'll construct the Galilean conformal algebra starting from the relativistic conformal algebra. And as an example, I will show you the Galilean electrodynamics case. Then we further develop the action formalism here, and we find the unique action for the Galilean conformal electrodynamics. Further, we study the dynamical structure based on the action, and then finally we end up with summary and future perspectives. Okay, let's introduce. So Galilean field theories are developed to understand the low energy physics, where the velocity is very small compared to that of light. And the Galilean space-time transformations can be seen by using c tending to infinity limit of the Lorentz space-time transformation given here. The main motivation behind the study of Galilean conformal field theories are the natural enhancement of symmetries, which leads to integrable field theories. We know that conformal field theory are exactly solvable in d equal to 2 dimensions, and but in general, high space-time dimension is not like that. So, but there are few examples like n equal to 4 superangles in 4 dimensions, and n equal to 6 Chern-Simons in 3 dimensions, etc. So first we can start with the conformal generators, relativistic case. So in d plus 1 Minkowski dimension, then the Poincare generators are here, and the conformal generators includes this dilatation and special conformal transformation generators. Okay, then we can construct the Galilean conformal algebra starting from the relativistic algebra using Inonu-Wigner contraction. So this contraction is done by taking c equal to 1 and the space-time scaling as xi going to epsilon xi and t going to t, or epsilon tending to 0. As an example, I construct here the boost generators. Boost generators in the Galilean case is defined as limit epsilon tending to 0, epsilon times the relativistic boost generator. It's here, and all the Galilean generators can be written like this. Okay, and after that we can construct the Galilean Lie algebra. Before that, we can organize generators in a more suggestive form as here, where ln and min n equal to -1, 0, 1 takes values for these. Ln's give you h dk, and n equal to -1, 0, 1 for min give you pi, bi, ki. All generators except this j rotation generators can be organized as this. And this algebra is a d plus 2 into d plus 3 by 2-dimensional Lie algebra as finite Galilean conformal algebra. And some properties of L's and Mi's. These transform in the scalar and the fundamental vector representation of the rotation group SOD generated by Jij. And this algebra close for all integer values of n and m, not only for -1 to +1. And this embeds the finite GCA into an infinite dimensional one. So this enhancement of symmetries in Galilean conformal theories in higher dimensions can extend to integrable theories. As an example, let's study the Galilean electrodynamics case. So Galilean electrodynamics was developed in 1973 by Bellac and Leblon. So they were trying to answer these questions: what are the Galilean limits of Maxwell's equations and Lorentz force if they exist? How do the magnetic and electric fields behave under Galilean transformations? And also they were curious to know about the equations that could have been written in the 1850s by a physicist trying to embody the known phenomena of electromagnetism in Galilean theory. And their observations were, instead of a single non-relativist limit, there are two limits called electric and magnetic limits, depend on the dominance of electric and magnetic effects. This we can see from here. The equation, when c tending to infinity, we can take either mu 0 or epsilon 0 tending to 0. And in past years, Galilean electrodynamics was explored in 4 dimensions, but Galilean conformal electrodynamics started to become popular recently. And regarding these limits, we can approach these limits by using the scaling of space-time coordinates as well as the difference in scaling of the gauge field components. So this is the relativistic case gauge field mu. So we can take the temporal part AT and AI separately in the non-relativistic case. These two limits can be expressed as in the electric case. This dominant part is the temporal part of the gauge field, and magnetic case the dominant part is the spatial part of the gauge field. Let's try to find the equations of motion here. So these are the relativistic equations of motion. T mu equal to del mu f mu equal to 0, and for temporal and spatial part we can construct this from here. And when you try to construct the Galilean equations of motion, we get 4 equations for total 4 equations for electric as well as the magnetic case. Okay, now these equations are invariant under the Galilean conformal symmetry in d equal to 3 space dimensions. And the next question to be asked is, given a set of equations, is it possible to find a Lagrangian corresponding to them? So this problem, known as inverse problem of calculus of variation, has been already studied in mathematical literature. So there are conditions called Helmholtz condition, which are necessary and sufficient conditions for the existence of action. So I briefly tell these. These are the Helmholtz condition. These equations of motion should satisfy these conditions in order to have a corresponding action for those equations of motion. Okay, so after that we try to find the action formalism using the Helmholtz criteria, but we failed for the both magnetic and electric sectors of Galilean electrodynamics. Then further we developed a consistent algorithm. So the algorithm is given here. Step 1, first we will pass the equations of motion through Helmholtz criteria. If they satisfy the criteria, we go to step 4. Step 4 is here. Step 4 is for checking the invariance of the equations of motion under Galilean conformal symmetry algebra. If you get a set of equations of motion which are invariant under step 4, then you can go to construction of action directly from here. And if you fail to get equations of motion which are invariant under Helmholtz criteria, you have to go to the step 2, where you have to add extra fields to the system such a way that these fields should have a well-defined Galilean conformal rules as well as the equations, and these equations should satisfy the Helmholtz criteria now. And step 3 is if you switch the fields to 0, extra added fields to 0, you have to get back the original equation of motion you have started with. And further, step 4, checking invariance of the equations of motion under Galilean conformal symmetry. So if you get an set of equations of motion which satisfy all these criteria, then you can go for the construction of action directly from here. Using this algorithm, we have constructed unique action for the magnetic sector of Galilean electrodynamics. Finally, we end up these equations of motion which are invariant under the actions of min and L-1, L0, L1, not all n, Ln. From here, we construct an action. This is the action constructed. And we tried the same procedure for the electric sector of Galilean conformal electrodynamics, but we couldn't find action even if we added extra scalar fields or vector fields. And for Carolean electrodynamics, we have found out the action for the magnetic sector of Carolean electrodynamics using the same procedure and reported here. Now, regarding the dynamical structure, using this action, we have found out that these action Lagrangian enjoys the following gauge invariance given here. And further, we went for the constraint analysis, and we end up in 0 physical space-time dimension of the theory. This makes it a topological field theory. And summary, we have constructed an algorithm to construct an action from the equations of motion of a theory if exists. Using this procedure, we obtain the unique action for the magnetic sector of Galilean electrodynamics with the addition of extra scalar field, and the infinite dimensional group of global Galilean conformal symmetry enjoyed by the equations of motion gets broken due to the inclusion of an extra scalar field. But the symmetry algebra still remains an infinite dimensional subalgebra of the Galilean conformal algebra. And we shown that it's not possible to obtain Galilean electric sector, equation action for the electric sector of Galilean electrodynamics, and we have studied the dynamical structure, and the Dirac constraint analysis shows that there are zero propagating degrees of freedom for the system. And future perspectives are regarding the study of quantization of these fields, and checking for the invariance of these conformal symmetries, infinite dimensional conformal symmetries. And another thing is supersymmetric field theories, construction of supersymmetric field theories, in this case both classical and quantum level. Okay, that's it. Thank you.
Thank you for the talk. Are there any questions? Be happy to